our website.
Cool, I consent. Yeah, so the paper is from, I think, well, the paper is how neural networks extrapolate from feed-forward to graph neural networks. And really, the way that they define extrapolation is when they learning outside the support of the training distribution.
If you press present, my apologies. Will it work for you, or you need to see the notes?
Oh boy. So I'm gonna be switching back and.
Oh, no. Oh, okay, that's fine. That's fine. Maybe there is a way to zoom in or like some.
Yeah,
I don't know. I don't know. I can see. I can see personally. I can see everything well, but yeah, that's fine. Let's continue. Sorry for interrupting.
Okay. The thing is, I feel like switching back and forth is probably the best thing for this paper. Yeah, so extrapolation in let's just talk about this in layman's terms, learning outside the support of the training distribution. They do this experimentally by sampling differently, but we'll get to that later. Interpolation is where we learn inside the support of the training distribution. And so what they're curious about is that neural networks, they theoretically have a high capacity, they're universal function approximators, but they don't do well in a whole bunch of tasks, and sometimes, very sometimes, they do okay. And then in graph neural networks, they have other successes. But why does this happen? And so what they do is they use neo-tangent kernel theory and a lot of experimental results to come to a couple conclusions. One is that ReLU MLPs trained by gradient descent converge to linear functions from the direction of the origin at what I presume is an extremely high rate. The second thing that they come to is that MLPs extrapolate well when the task is linear and the geometry of the training distribution is sufficiently diverse. And that goes back to the support of the training distribution and the dimensionality and et cetera of what that means. And then finally, they have a hypothesis that they semi-do a proof for, that graph neural networks extrapolate well on certain tasks because of linear algorithmic alignment. The experimental tasks that they perform.
Can you quickly say what is linear algorithmic alignment there? What they mean by that?
Yeah, so their hypothesis of linear algorithmic alignment is that basically if you transform the inputs to a space that either through nonlinear transforms or through some other transform, and by that I mean the recursive learning or some other activation functions, then they can extrapolate well because that space is, you can extrapolate linearly from that space and still do okay, is what they're saying. And they also provide, they also say that interpolation can happen in these spaces, but not extrapolation, essentially. So like if you have the wrong space, if you have the wrong encoding, whether it be through architecture or through feature transformation, if you have the wrong encoding, then you can interpolate well in these regimes, but you cannot extrapolate well. They do this experimentally on a couple different tasks. So they learn functions for these 2-layer and larger, basically architecture searched MLPs for tanh, cosine, quadratic, and linear functions, as well, linear being straight linear as well as L1 norm. And then dynamic programming tasks for the graph problems. Max degree, shortest path, and body problems. Note, so I'm probably not going to be able to explain the neo-tangent kernel theories very well in the appendix. It's extremely large. But so the first theorem is that suppose you train a 2-layer array MLP with squared loss in the NTK regime. For any direction v within that real, let x equal tv, and then as x goes to infinity, and as the functions go for any h greater than 0, Jesus Christ. Yeah, so 1 second. My internet connection is unstable. We can go into the paper for this because this is very tough for me. And we can also say do what they say in the paper. So, boom, boom, boom.
Yeah, if anyone wants to help, like just translating the theorem, please, you're welcome to just jump in.
Please, you'd be very welcome at this point. Because the experimental is very easy to say, but this is less easy to say. So
do you want to scroll to the theorem in the paper, or what are we doing now?
Yeah, we're scrolling to the theorem in the paper. We go past the definition of NTK, we go past the definition of the other things, and then we go to the definition in the paper where boom, boom. So there are linear coefficients, beta v. There are constant terms in convergence for the direction, which is v. So this is the direction, v. X is the input, I guess, or function for this. X is the input. T, I'm not entirely sure what T.
Isn't the idea that they're like going, so you have like a d-dimensional input, and then if you go in any direction in that input, then you want the difference in the output to be like the last part. You want it to be smaller than eta or epsilon.
And why are they going from the origin? Is the training data around the origin? Is it the property of NTK training regime, or what is it? Like they're going away from the origin. That's what they say.
Yeah.
Or is it just a center of mass and we can always normalize?
I think the idea is just that you start at 0, 0, and then as you go like along that dimension, so it's kind of like going only in that dimension and not going in both dimensions, for example. It's not like
oh, they say any direction, so I think it's just a general vector.
Yeah, but I mean, okay, but I mean, like if you have a 2D plane, they're saying only go across the x-axis or across the y-axis. Do not go like in a diagonal line. That's what they're saying, I think. Like in this case.
No, v is any direction, right? For any direction v, so it could be anything. Like
okay, I interpret it as like along one dimension.
But yeah, I think it could be anything. But the figure
one dimension isn't one coordinate, because the coordinate is kind of arbitrary.
I don't think it's. I think it's any direction, but I'm confused as to.
Well, in the middle it says any direction, right? For any direction v.
Oh yeah, you're
but
right.
Can you show the figure? If you show the beginning, like the figure, it will be clear what they mean. I think I'm visual, so the next one, the previous one, sorry.
The previous one, sorry.
Figure 2.
Figure 2.
Yeah, figure 1 actually. Yeah, look like.
Okay.
Yeah, figure 1. The how lose MLP extrapolate this one. Yeah, like that's what they're saying. Anywhere you go from the blue region, it becomes linear. Like any direction you go, the output of your prediction becomes linear, no matter what input is. So that.
Yeah,
Yeah, and I think they started the origin maybe because that's where the most sort of mass is, like that, because it's the middle of your data distribution mass or something. I don't know.
Well, yeah, I think you can always renormalize, right? You can shift your origin to the center of mass, and then you work with those vectors.
I've done some sort of with just real-to-real functions. So this is like higher dimensional than what I was doing, but I did a similar thing, and I noticed that at the beginning of the learning process, it converged along like near the origin, and it would learn farther and farther away from the origin, sort of like in a Taylor expansion. The first approximation is valid near where you choose your initial point. And that's the origin, probably just because of the way that the architecture is set up. Whereas if you set it up as an affine thing, then maybe it would be different, where you like embed it into a higher dimension first. I'm not quite sure, but
you didn't use bias.
Sorry. Yeah. Yes. Exactly. Yes.
I think it's also to do with like how they sample from the original function. Like I think they sample near the origin.
They sampled basically, yeah, they did sample near the origin.
Well,
but you can just define the origin as wherever the center of that distribution is, I feel like. But that's...
Or
like,
wherever
that's
the origin is in the input vector space.
Right, exactly. Because you're doing like a quadratic function. So you have like x squared, for example, x plus y, x squared plus y squared. And then you just sample like around 0 for x and y.
Well, but this is a picture and simulation.
It does make sense.
The theorem is general, right?
Right.
Not just about the simulation.
The theorem is general, like for two-layer MLPs, and they're trying to go beyond that.
Okay, I think if we go back to the theorem, we will just understand it now, right? Like after looking at the picture.
Wow. My
off-topic questions. Are you on X11, Xorg, or on what's the Wayland?
So my int did what you wanted. I think my internet's back to normal.
yeah, it's fluctuating.
Yeah, so I guess I don't understand exactly what this means precisely. Like,
oh, it's just the bound, or like how fast the difference. It's just the difference between the coefficient.
The difference between the coefficient.
Isn't it sort of like isn't it kind of like the gradient?
It does look to me like a finite difference approximation of the gradient, but the gradient, yeah, exactly. The gradient in the linear case will be just beta, and so the finite difference approximation of the gradient in the general case for f is on the left.
Okay, so it's the difference between the gradient and then it converges. Okay.
The highlighted is the gradient, well, the gradient approximation in the general case, and the beta sub v is the actual gradient for in the linear case.
Oh, okay.
And what's h?
It's your step, right? The usual.
Okay.
Yeah.
For any age greater than 0. So you can choose your step, and then you'll find an epsilon. Oh, for any epsilon. Eventually, it'll become less than any epsilon. That's what they're proving, right?
Okay. So that means that it then converges, like basically it doesn't go outside of this, outside of the distribution. Once it gets outside of the distribution, it does become, it does linearly extrapolate essentially. That's what it's saying.
That's the gradient. Yeah, the gradient becomes linear, or
because the gradient becomes linear.
I don't know. Then it doesn't become linear. It's like speaking about like Taylor expansions. Jack pointed, but it will be very close to linear. So.
Okay. All right. Yeah, and so that's the first theorem. Experimentally, and we can take a look at the graphs, but experimentally they extract. Go ahead.
So let me just make sure I'm kind of understanding so like, because it's similar to a Taylor expansion, does that basically mean that like when you have regions of the possible space of data that are lacking data, that it can't extrapolate in that region because it can only extrapolate linearly over short distances in that space because the is doing it in like a piecewise linear fashion or something like that?
Well,
I don't think there is piecewise there, but otherwise.
It's not piecewise, and it should always extrapolate linearly. It just means that, for instance, if you don't have support in a direction, then it's going to go linearly no matter what. So say that your like training data is not linear and you don't transform it to be linear, then you can interpolate well inside that. But once you get outside of that distribution, you're always going to be linear.
Okay. So can you would it be accurate to say that neural networks can handle nonlinear data if they have a lot of data, or do they even fail in the case where there's a lot of data?
So I apologize, my internet looks awful. But so when they when they do the experimental results, at least for interpolation, meaning within they have a lot of data, they get fairly low. They get fairly low MAPE, but when they do extrapolation, it goes poorly.
Okay.
So, William, based on your question, just a quick comment. The way I think about it may be wrong, but it helps me to understand what's going on. If you take your data set and build a convex hull around it, so interpolation is when you're trying to predict the points within other points that are not in your training set, the points within the convex hull, and extrapolation when it's outside of the convex hull, when you're trying to predict their values. So that kind of makes sense. So it doesn't matter how much data you have, but it's like within that ball or whatever and outside that ball.
Okay.
Also,
Yeah, agreed.
I don't know if this is true for all neural networks. I mean, obviously they're starting to build this theory for ReLU MLPs, which are basically like the most simple. So it's not really clear whether this holds for like the general.
Well, they
like
had an
if you're talking
interesting
about neural
argument.
networks.
In the talk, at least, he mentioned that an interesting argument that we know that ReLUs are basically shatter the space into piecewise linear regions. And there is a asymptotic argument that eventually, because we only have finite number of hyperplanes that a neural network like that can build, we will run out of possibilities that it will be shattering on only a small region of it or something, and the rest outside will be linear. But it's an asymptotic argument, and here they're trying to give like a direct demonstration that you don't need to even use any asymptotic argument. That happens right there, right then.
Yeah.
No, I agree. So I think you can think about it like that, but my point was more like the proof itself says specifically, suppose we train a two-layer ReLU MLP, which obviously constricts the space of the amount of neural networks to a very specific case, which is like, 2 layers is only a few piecewise hyperplanes. So I'm not saying you can't prove this for all neural networks. I'm just saying that although this may be general, it is also good to, it doesn't have to hold for all neural networks.
I like your comment. Like math is a tool to gain intuition, right? And we have to make some sometimes very severe simplifying assumptions. And it's not only about two-layer ReLU, it's only about the specific way to train it, the NLTK, NTK regime, the neural tangent kernel regime and stuff. So they had to make assumptions in order for the proof to work.
I mean, I think basically it comes from the activation functions. And this is just an intuition from when I was playing around with this sort of a thing. If your activation functions are only nonlinear in a small region of their domain, then you're always going to have this property, is my guess. But if your activation functions are nonlinear over the entire domain, then you're not going to have this linear extrapolation property.
But then how do you, like,
I don't understand.
How do you train this?
Well, my intuition as to what Jack was saying is like, okay, a ReLU MLP creates these piecewise linear hyperplanes, but that's also because of the ReLU, of like what the ReLU is as an activation function. We don't know if this is true for, like, let's say 10H activation functions, or, you know, more complex activation functions. You know, because it may also be caused by what you're saying. It's piecewise linear, so that may also cause this linear extrapolation problem. Whereas if you have activation functions that do not have piecewise linear that do not cause like piecewise linear hyperplanes,
yes,
then we may not have the same problem.
Tan H though, when you move to the asymptotes of the function, then it's basically a constant. So you can only expand that region of curvature or nonlinearity finitely far unless you let your parameters of your model become infinite. Like, you're only going to have a nonlinearity in a region that depend, like, if you only have nonlinearity in a small region in your activation function, you're not going to be able to make that nonlinear over the entire domain in your complete model.
No, I guess a tan H was not a good example, but I'm just trying to say, like, trying to ground, like, I agree with you that maybe this is also caused by the activation function they chose, which we know is only nonlinear in very specific domain for the input.
At one point, basically.
Yeah, well, but exactly. If you notice, all of our nonlinearities are kind of weakly nonlinear. They're like everything that we use are nonlinear around zero, but it doesn't mean that we can handle the data outside of like the zero region. And plus, we can always normalize, and the weights do that renormalization. Like the stan H can be stretched by the weights such that your data is still within the nonlinear region. It's not at the constant tails, for example. So I don't know, Jack. I'm having trouble with maybe just not enough imagination, like imagining of why would that matter? Because all of our activations are kind of interesting, have interesting behavior only around their zero, but because preceding transformation of the data, you can always kind of munch the input data into that region anyways.
Right. Yeah, I don't disagree with that.
But if we would have truly nonlinear functions over like the whole domain,
like sine,
then
yes.
Right, then maybe we could create spaces, like, you know, that's more of the point. Like, I'm not saying that it's like practical, but, you know, maybe if we did have them, then we wouldn't have this problem, because it may also be like, they're not truly nonlinear in a way. You know, there's only like, like, for example, exactly. ReLUs are not truly nonlinear.
Well, let's call them weakly nonlinear, right?
Okay, right,
they are.
Like, they don't have to be, though. I mean, if all your data input is always above zero, it's just a linear transformation. Obviously, it's learned, but like.
But the nonlinearity just I think it might be important comment. Non-linearity affects the training dynamics. So you're not learning like a one giant linear transformation, or at least, I don't know, maybe.
Oh, I
If
agree.
you were
I
learning
agree.
if you were learning a giant linear transformation, you could like condense all of the arrays or the tensors into one tensor, right?
If it is, but then, yeah. Well, anyway.
I didn't get William's last question, but
I might have been commenting on something that wasn't being talked about, but like it seemed like you were kind of discussing whether ReLU was essentially linear, like all in effect. But I was basically saying that I think like the properties in linear algebra say that if you multiply a bunch of tensors together that are linear, you can replace that series of operations by a single matrix operation.
oh, okay.
Yeah.
Okay, so in addition to this, they talk about, they experimentally verify the extrapolation of linear and L1 norms, and then also the failure of extrapolation for the quadratic cosine and square root functions. And then they do this for across a number of different widths, depths, learning rates, batch sizes, etc. We can, and so that's why these plots look a little bit interesting, is because this is across a number of different network training parameters essentially. And so anything basically fairly low is good, and anything fairly high is awful in that sense. And so this is just just experimental verification on that.
It's funny that for quadratic functions, it doesn't matter. Like it's always kind of bad, and for every type of run. But then for L1, it's just like it can be either really good or really bad. Like it's super all over the place depending on the hyperparameters.
Yeah. And then the next bit of this, the next graph of this actually follows with the point that we were making about the support of the training data and essentially the directions of the distribution. So basically it has to include all directions if you want it to, if you want your network or your ReLU MLP to extrapolate well. Otherwise, it's going to do poorly. And so I think that this graph is the illustration of that, where if you fix it in a single dimension, then you do worse, obviously, than if you eventually cover all the directions. And so this is just seeing how you fix the different dimensions and how that affects the training for ReLU MLPs.
Yeah, that should be sort of, I guess, obvious though, right? Because there's an infinite space of functions that could be totally different. If you're only looking at one subspace, then I don't see how you can extrapolate outside of it in general.
Yeah. It's not like entirely. It doesn't seem it's not obvious, I guess.
Yeah.
Yeah. But it's just more constraint, I guess. More of a constraint, which makes sense to me. And then this is more of the plotting and more of the dimension support that we mentioned earlier. And then they do experimental results for MLPs with non-ReLU activations. And then they find that MLPs extrapolate well when the target and activation functions are similar, and each function has different limitations. And so this is things related to tanh, where it has to be a sufficiently wide distribution for that to work. And then for a quadratic function, it needs a depth of 2 or greater. And there are results for this illustrated on this graph as well. This is essentially, again, acknowledging your activation function has a large effect when coupled with your training data.
It's weird that the quadratic activation works the best for linear.
For the quadratic activation, the number of layers that matter.
Well, it's more that it's surprising that 10H cosine do not perform well on linear and perform better on their respective tasks, so to say. But then quadratic activation performs better on linear, or some runs perform better on linear than on the quadratic task, the quad 2 task.
So the weirdness is that linear can be learned with quadratic functions.
But not with the others. Worse with the others.
Well, it would I'm not entirely worse with the others makes sense to me, but I don't understand quadratic too well. I think that's
the error again. What is the MAPE?
Mean average percentage error.
That error is measured again as L2. Could that be because L2 kind of fits the quadratic better, right? I'm just trying to generate hypothesis. Why could that be? Like with cosine, you get a little phase shift and you're in trouble. With quadratic, that is not as much of a problem. Tan H, I'm not sure. Because you're measuring your if again. Okay, let me go to the paper and see what it.
Can I add something? I think if you make the quadratic very wide, it becomes almost linear. Maybe that's it. It's easier to approximate linear.
Right. Yeah, that makes sense. But I think that makes sense. I'm just also surprised that 10H and cosine activations are that bad at learning linear. For cosine, it kind of makes sense, but like Jack mentioned, for 10H, there is a region on that activation that is almost, like a constant. So.
Yeah, but the nonlinearity, at some point, it squashes in those functions, right? So, compare if this is extrapolation, yeah, it's extrapolation, then that's exactly where it's gonna fail. No, in comparison to a quadratic, it will not squash, and then this is hand waving.
I think maybe the gradients just
I
get
think that
for the tan H and not for the quadratic.
Do you guys want to see the exact experimental details for tan H and cosine, I guess? Or we
not
can...
necessarily. I thought Roger's explanation was pretty logical. Let's say you learn this linear activation, right? And then you may get 100% sort of training, perfection, right? So the error is 0 for your training set. But then you start to extrapolate and you're not in this, let's say the 10H looks like this, and you're always in this region. As you start to extrapolate, you'll find yourself the points going in this non-linear part of the function, and then you can't, extrapolate well for the linear, function that you're trying to learn anymore. I think that's sort of what Rogers was trying to say, right? You learn all these points, you learn this linear function by putting all the points in this sort of more linear region of your tan H. But then as you start to extrapolate, you go to the nonlinear and it squashes all the points together, and then you're kind of then obviously you're not going to do well on the task.
Yeah, I think that makes sense.
Yeah, and maybe you could, maybe it goes back to like some measure of strength of the nonlinearity. If it's too strong, it breaks down faster, I guess.
And also maybe the domain, like how large is the domain, right? Of the activation kind of, that may also, because like you said, the quadratic function, the quadratic activation may not have a very, like it's weakly nonlinear on a larger domain, whereas the 10H is very strongly nonlinear on kind of the, I don't know.
Where my mind goes here is there a way, like just a rhetorical question that I don't know the answer to, but is there a way to make the decision of what activation to use part of the computation graph so it can be learned?
To
Do you
make
mean using
Symbolic
these,
AIs.
I heard too many people at once.
Yeah, let's try the Ethernet protocol, random access, whatever media broadcast. So what was the question? What can be made as a part of computation graph? What can be learned? What do you mean, William?
Since it's clear that different activation functions have different results on different problems, I would think it would be useful to, and part of architecture searches, discover what activation functions you should use, but I can't think of a way to make the decision on what activation function to use a learned thing. It seems like it's something you would learn with evolution or some sort of search that's not part of the computation graph, which is inefficient.
Or use an just as a joke, or use an ensembled activation function. But the problem was that ReLUs became popular because they were so easy to train. They finally started converging quickly and everything. So everyone, the field switched to the ReLU because of that.
I mean, we've been talking about failing in the linear case, right? That might be too much of a corner case. I have two comments on that. One is, do you really expect things to be linear outside of your, what's it called again? This ball? Thought there was a name for that. But I think you understand.
Training distribution, the domain, the training domain.
Thank you. Yeah. So do you expect that to be linear is one thing. And the other thing is, I don't know, maybe you can, in the case of the 10H, for example, you could cancel it out maybe with another.
Well, can I be a devil's advocate for linear? Let's bring up this magic widget, which is shiny and nice, which is called Occam's razor. Let's put it on the table here and think about the following: like, if we start hypothesizing and drawing dragons outside of the map that we visited, just like trying to be highly nonlinear, is that a good approximation, or it's a better approximation to assume that whatever was at the corner, at the border, just continues like that? Which one is more Occam's razor style and spirit?
I mean, in general, there's no way to say. I mean, there's certain functions which are linear in some regions and nonlinear in others, and you might have one of those which is linear in the region of interest and nonlinear in the region that you might, or it's linear in the region where you have data and nonlinear in the region where you don't. And you might have the exact opposite, where it's nonlinear in the region that you don't and linear in the region that you do. Did I say that right? But yeah, anyway, I think the point is relatively clear. There's just like no general measure on functions that you can assume that.
But maybe their synthetic data, their examples, just kind of too simplistic. But like in the complex world where we had to introduce Occam's razor for philosophical reasons, how do we know, like, is it better to just like stay with our knowledge about, well, the black swan thing, right? There is no way to say, why would we hypothesize stuff? I'm just trying to take it to extreme. So instead of their extreme is the most simplistic functions, but let's take it to a different extreme and analyze it on those corner cases. What is the best strategy for our AI learning agent? To just stay with like safe, to play it safe, and as soon as it changes, adjust, or to like continue all of the non-linearities that has been seen in the training data. What's the reason? Like, as you said, Jack, I totally agree. It's like, what's the reason to assume that my sinusoidal pattern that I see right now is everywhere sinusoidal? Is it a safe assumption?
I'd say that the answer is kind of in between. And I'm not sure that Occam's razor is the best principle to invoke here. Because to begin with, your training data has no evidence to support linearity. It's assumption because you had to use a nonlinear function to fit well whatever you're trying to do, whatever function you're trying to approximate. So linear didn't work to begin with. So you have no prior evidence from your whatever data you have, even if it's not good support. It's the evidence that you have, and it has no evidence for linearity in there. Maybe.
Well, but maybe our learning theory is wrong, because the best predictor of the future is just a constant function of what was there today, right? Which is like the linear in the most extreme sense in the world.
I think that is true if you have no priors, but the moment you have data, you have priors. So you go by the evidence that you have, I think, not by ephemeral principles that are not based on the data that you have. Even if your data is biased or incomplete, it's some evidence.
Yeah, so I'm more in favor of like what Roger says, in that ideally you would like the training data to help you go towards some prior or go towards a distribution, and that just disregarding like your training disregarding your domain and just saying, okay, once I'm out of that, I'm going to only go linear. Well, I'm only going to error linearly is probably right for disaster.
Like I said, I didn't mean like it will be highly nonlinear as the training data was. I meant to say that it's probably somewhere in between. That you needed some nonlinearity to solve the problem up until this point on the data that you have. Probably gonna need some of it outside. How much? I don't know. Maybe it's a smooth interpolation, extrapolation in that sense. That maybe the farther you go from your training data, maybe the more it makes more sense. The farther you go from the data, it makes more sense to invoke those general principles, maybe Occam's razor and the constant approximation when you go really far out. And in between, maybe there's a class of functions that behaves that way. It's nonlinear and becomes slowly linear towards infinity.
Yeah, I mean, I think this has to do with also like, oh wow, there's a whole bunch of stuff here. I essentially just agree with Roger's thought, but this is again showing that ReLU MLPs, and then he, during his talk, generalizes that to CNNs and RNNs, have the weakness of linear error in their extrapolation regime or outside of their training data.
So basically what I was trying to say, and that said in the chat, and Eloy responded to, is that like what everybody already knows and probably has already said, but then that like if you talk about calculus over a sufficiently small interval, all analytic functions can be approximated linearly. And then Eli was basically saying, but you don't want to just approximate things over small intervals. You want to extend that interval. And I think that's probably a valid point as well. So, I mean, I could see that in any neural network that you're evolving over time and then gets passed around to the scientific community involved more for specific problems, I could see like activations becoming like maybe having an assumption of linearity as a starting point, but then like evolving to having more complicated activation functions as people work on the problem.
Well, what if we think about a concrete example of maybe like, let's say you had to learn Newtonian mechanics. I mean, from, I don't know, balls colliding or just some sort of input time series. Like, how do you get to that general principle in general? Like, what kind of general principle would you have to discover the underlying rules? I mean, I don't know what the answer to that is, but it seems like we've been able to do pretty well at that in certain areas, but I don't know in general why. That's kind of it's a very interesting question though.
By we, you mean humans in terms of like making Newtonian mechanics equations?
Mm-hmm.
Okay.
I also
We're
want to
actually
add, like, to add on to Roger's point. To me, this also kind of shows, and oh, sorry, my internet?
no, go ahead. But humans are terrible at that. Actually, think about the physics experiment with a pipe, with a circular pipe. Humans overdo what you think the neural network should do. Exactly. Humans continue that wavy pattern to infinity. Take a pipe, put a ball in it, and pipe is circular, and the ball speeds through the pipe, and then the pipe abruptly stops. And ask 1,000 humans to draw the trajectory after the pipe stops, and most of them will continue the circular trajectory. Because
Right.
that they do exactly what they shouldn't done. They don't use Occam's razor. They just extrapolate. But the trajectory after the pipe ends is linear. I mean, I'm continuing to wearing my devil's advocate hat. Sorry.
Is that rock Occam's razor or not, though? It's an interesting question too.
I thought it's something kind of obvious that nevertheless kind of made me excited. So like the like one thing that might be useful in determining activation functions maybe is like if you're making a bad assumption in your activation function, you're assuming linear properties, then you're going to need a lot more data to make that piecewise linear enough to actually get it right. But if you like basically decide, okay, gravity is not linear, it's quadratic, and so if you change your activation function to quadratic, you could probably have good accuracy with less data. Maybe that would be some sort of signal that you could use to figure out what activation functions you need.
I kind of want to add on to that point, but also to Roger's point. Isn't it also these results also kind of show that if you know your data well, if you analyze your data well in advance, if you have a basic good understanding of what type of kind of data you expect outside of the data you've gathered, obviously that's really hard to hypothesize, but like we're talking about neuroimaging data, for example. Like if you have a good prior about your data, then you should choose your activation function based on that prior. That's basically what I kind of get out of this picture as well. This figure is like, if you know like a 10H activation, if you know your data is going to be kind of like a 10H, then having a 10H activation is just going to be so much better. Like, how does your nonlinearity, what do you expect the nonlinearity in your data to look like maybe you should match that with the activation you use in your neural network.
Yeah, for a physical system or for like an equation that we know that something is going to happen, you should do that.
Or at least closely match it. Try to match it like kind of as closely as possible. Because you can see, for example, the cosine activation performs better on the 10H, which in some sense makes sense, right? It's like a R cosine. So.
And then there's the whole Bayesian prior argument that priors should influence on the outputs of your results, and you should have confidence bounds that are influenced by that, and outputs that are influenced by that. And MLP ReLUs don't do that, is basically what's being shown, which is fine. It's just good to know.
Well, I like the Bayesian prior argument, but I think there's a problem with it because it doesn't account for like where the networks can't model like translational invariance of that prior sort of. Yeah, the Bayesian priors works right in the domain where I saw the data and I didn't have samples anywhere outside. My prior there is actually flat, or yeah, like I don't have any prior there. So if the point I think that Rogers is making is more subtle than just an architecture search. It's
Oh no, I agree. But I think the whole point is more like you should take your training data and assume that is at least kind of correct. That's how I interpret the argument. Like you can't just say, well, I don't know anything, even though I have training data, because it might be a steeply nonlinear function just outside of my training bound. Because that's kind of like Occam's razor, right? I mean, to take it to the extreme.
Yeah, but if you operate in the geometric domain of their examples, then the prior there is no way to tell that this prior translates, because we were sampling here and my prior says that outside there is nothing. So we need a new architecture, new approach, like a different way to say, okay, well, or reparameterization of the space where that prior is defined, right? That when you translate around the parameters in some space, not in the space where the data is defined, it still stays the same.
But like practically for neuroimaging data, we have so much more prior than just the data that we obtain. We know kind of like how on a smaller scale, for example, neurons operate. You know, not perfectly, but we have.
You're talking about inductive bias that we need to encode in the model.
Well, I think we should take the training data, everything that we have about the data. Like we've gathered so much more about the brain, for example, than just the training data. So we may have a better idea of what everything may look like outside of the training distribution than for a function like this, for example, where, you know, if you just give it to the network, it doesn't know anything. You know, it's just going to be like, oh, I don't know. But let's say you have this problem that they have and you choose the 10H function because you know that your data is probably going to be like that because you take, you know, neural networks are also kind of engineering. Like you need to take everything into account. Like what, I'm not saying you should do an architecture search, but like based on everything that you know about the brain or everything that you know about neuroimaging data, you can make a better decision as to what activation function to use. I think that is also like it's kind of like the same, like in some ways the same as Roger was saying, because Roger was saying like you should take the training data and just kind of assume that that is correct. And in that sense, if you do that, you can maybe also take a better activation function. I don't know.
With a certain bounds and with a certain decay, right? But yeah, from the direction.
If I may add something, I think it links to what Sergey was saying. When you go out of the sampling distribution, you just break your prior, like whatever prior you had doesn't work. But with, you know, in that case, just need to be a little careful because it's like you're retraining with new data. And we're back to square one, I think. So the idea is you don't have ever that information and you somehow make a good prediction. we can test the outcome, but then going back and changing the network to do better on new data, then it's like solving the problem. It's going back to the beginning again, is what I mean.
Kind of late in the game, but today I need to finish right on time, which is now. I will assign Kevin the host and leave, but it was fantastic discussion. I will post the video after that, so you can still continue, post discussion. So
Okay.
thank you.